Let's try another example. So there are two plots here. On the top, we have the function. So this is fx. And we want to draw its derivative f prime x just by looking at the plot. Okay, so we just look at the slope of the tangent line, the steepness. So what do we have here? So we want to move from left to right. No, so let's go from the most left point is at -3. So what is the derivative at -3? So basically you want to draw this tangent line, right? And it seems to be because the curve is going up at at -3. The derivative must be positive. And it's very positive because it's very steep. It's a very fast increase. So we'll go, maybe that's, I don't know, 4 or something. Now, as you move along the curve, if you move along the curve, right, you can see that you still have very fast increase, but it's not as fast as the original one. It's getting slower. The increase is getting slower. That means you still have positive derivative, but it's getting smaller and smaller because the increase is slower. Now, at this point, this is -1, the slope is like this, the tangent line, right? So the slope becomes 0. That means the derivative is 0. Okay? And after -1, the curve bends, right? It goes downwards after -1. So if you go this way, the derivative becomes negative. All right. So what you can have is something like this, and it's always negative until you reach this point, right? Where the slope becomes 0 again. So between -1 and positive, so again we get a few key values. From here to here, the derivative is positive. Between -1 and +1, the derivative is negative. And then between 1 and 3, the derivative becomes positive again. Okay, so you should have something like this. Oops. I should draw this faster. And then between -1 and +1, derivative is negative. And we'll go like it's most negative at 0 because at this 0 point, this downward trend is you can see it's this downward trend is the fastest one, the fastest one. So you get most negative, and then it will go back to 0, and then it will just increase like that, something like this. Okay. The values are not very accurate because it's just a plot, right? You have to do real calculation to see so maybe it's not -2, maybe it's -3 or something, but this is a general trend for this derivative, okay? It starts with a very positive value because the derivative is very positive here, right? It's a very fast increase. Then at -1, it will become 0. So that's why you have this this point, this line, and then between -1 and +1, the derivative is negative because it's decreasing. So it's negative, but it's, this derivative is most negative at 0. So that's why it's the lowest point here, and then it will increase. Even though it's still negative, right? It's increasing because this decreasing trend is becoming slower and slower. After 1, the curve bend upwards, right? So it's increasing now, and that means the derivative become positive, and it's getting faster and faster. So that's why you have this part. So that's how you can make the derivative function, make the plot using just by visualizing the this original function. So this is how you do that. And next, I want to give you some new names for the derivative, some new notations for derivative. We used to say it's going to be f prime x, right? This is the derivative of the function. Another notation is you can do ddx, fx. That's the same thing. So that means you have the function fx, okay? When you do ddx, we are talking about the derivative of the function with respect to x. So this f is a function of x, right? And when you do derivative, you should do this with respect to x. So that's why you have ddx, dx. So these two are the same thing. F prime x is easier to write, but sometimes it's more convenient to do this ddx. And since we also do say y equals fx, right? This is sometimes we write y equals fx, and then if that's the case, you will have dy dx. So they are all the same. So if here, for the middle one, for the second one, some people just write ddx fx. You can put this fx either on the top, in the numerator, or you can write this fx after ddx. So ddx is what we call this operator. That means ddx will do something on fx, and that operator, this operation will be, let's take the derivative. Okay, so either this one ddx and then fx, or dfx dx. So these two are totally equivalent. Okay, it's just personal taste. You can do any one of these. If we label fx as your y, this output, you can do dy dx. Now, sometimes we say, I want to do fx, right? I want to find the derivative at some point, not just this general x. I just want to focus on a specific value a. So this is like the derivative, right, of the function f at a specific location a. Right, this is the one we used earlier, f prime a. So you can write f prime a, or you can do d dx fx. And we have to specify, so x equals a. We want to focus on this a location, so we just write something like that. Okay, we write this vertical line, then we write down, what value you want to specify to have the derivative as a subscript down here. Right, so these two are also the same. Or you may write, dy dx. If you just say, y is fx, then write x equals a, like that. So they are all the same. So these are the same. These are the same one. All right. Now, if you look at these two plots, right? The first one, the top one is fx. The bottom one is called derivative f prime x. Now, if you look at this, f prime x is actually a function, right? So it has value that can change. You have, you can draw the slope, and you can still do derivative for this f prime x, right? If you treat this shape, right, this function as, some function, and you talk about what is the derivative of that function. So basically, you are taking the derivative of the derivative. Sometimes we do that, and that's what we call second order derivative. Okay, if you try to do derivative, right? This is the derivative, and you try to do another derivative. So you put 2 prime here, f prime prime. So 2 prime means second order derivative. Right? Now you can do third order. You take the second order derivative. You still have, this is still a function. You can talk about its derivative. Look at the tangent line, the slope of the tangent line, and so on. So you can have third order derivative. And you can write f prime prime prime. And you can keep doing. But you don't want to write too many prime, right? If I give you something like, you have to count. This is 1, 2, 3, 4, 5. This is the 7th order derivative. That's not a good idea. So if you get higher order derivative, what you do is you just write a number for that. So for example, the nth order derivative, that will be f. I just write fn x. N means n primes. Okay. This is not, if n equals 2, you have f2x. Right? This is not square of f. This is the second order derivative of x. So don't be confused about that. Because of this, sometimes I prefer this. I write n, but inside parentheses. So that's nth order derivative. Okay. Now in our class, the most common value for the order will be 2. 1, right? 1 is f1x. Not many people use that. If you just have first order, this is just the normal derivative, you just write f prime x. Okay. For second order, I think f double prime is also common. And yeah, you can do higher, but we don't really go that high in this course. So first order, second order will be like the maximum we will do. But the notation is like this. Okay, so when you see that, we are talking about higher order derivatives.